trying to convey, what we're trying to talk about in terms of materials and power plants, because that's why we're here at King's. We want to learn about nuclear power and how we can use nuclear power to make life better for everyone. What we talked about in materials is what's different about nuclear power. How long have we had electric power plants? How long have we made the power plants? Anybody guess? 130 years? 130 years. We first had hydropower in Niagara Falls. It was close to where I grew up. So they picked out materials to build the plants for a long time. And a lot of it, we learned the best materials, and this hasn't changed in a long time. But there's special things happen with nuclear power, and people didn't learn. What happens when people don't learn about the mistakes in nuclear power materials? What happens? People die. Workers die, right? That's what happened at Mihama. Mihama Unit 3, 5 workers died, they didn't have to. And it's very expensive too, right? So we don't want to do that. We want to learn from the mistakes and not make the same mistakes again. So that's what we emphasized. And so what were the big nuclear problems that we saw? What are the names for those challenges, those problems?
Stress, corrosion, cracking.
Yeah, stress, corrosion, cracking. So there were a lot of steam generators thrown away. Steam generators are a very big thing and a very expensive thing, and it's even more expensive to replace, because when you build it costs one amount, but if you have to take it out of an operating plant and put in a new one, it's very expensive. Okay? So we had the wrong materials for the steam generators. So what was the material that was the bad material in the steam generator? The tubing was bad, right? We had to plug the tubes, and when all the tubes are plugged, you have to get a new steam generator. So what was the old material for the steam generator tubes? What was the name of the material? Inconel 600, right? And then they did what? They called Inconel 600 TT. Does anybody know what the letters TT stand for? Thermally treated, right? So they would relieve stress. Why do we have to relieve stress in a tube? Did anybody watch the video for feed water heater tubes? It was on the list, okay? So we do annealing of the tube. When do we anneal the tube? What do we call it? A U-tube steam generator. How do you get a U-tube? Take a straight tube and bend it, right? So after you bend the tube, what do you have? Residual stress, okay? How do you get rid of residual stress? You heat it up, and then the material finds a good shape, and then you let it cool off, and it doesn't have residual stress. So that's thermally treated. But even 600 TT wasn't so good. So now what do we use? What's the name of the new material? 690. What does 690 mean? Inconel 690, right? 690 TT, right? So nobody does this and nobody does this anymore. We all do this, right? So that's, some people say IGSCC, some people say PWSCC, and some people say IASCC. Anybody know what those, SCC is stress, corrosion, cracking, right? So what's the PW? Primary water, right? How about IG? Intergranular, right? Between the grains. And how about IA? We didn't have enough. We only had 2. We needed another one, right? So for nuclear, they threw it. This is already a nuclear one. They threw in another nuclear one. Irradiation accelerated stress, corrosion, cracking, okay? So if you have irradiation, it might go even faster. Okay, so let's forget that. What's the other big problem we have with nuclear power plants? Back, right. And that stands for what? Flow accelerated corrosion, right? And what material had a problem with FAC? Carbon steel, right? So now what do? How do we fix that problem? We add chrome, right? So we have carbon steel, 0.2% chrome minimum, right? That's the minimum amount. And what's the maximum? You're the designer. You're the purchaser. You say, I want 0.2% minimum. Who says the maximum amount? Do you also decide the maximum? No. Who decides the maximum? The materials code, right? ASME section 2, ASME boiler and pressure vessel code section 2, or ASTM. And depends on the carbon steel. It might be 0.3% max or 0.4% max. It depends on the material, but there's a maximum chrome too, okay? But that's decided by the code, okay? What else? We might do P11 or P22. What's that mean? What are those? Alloy steel. What does alloy steel mean? We start with carbon steel and put in extra, in this case what? Chrome and molybdenum, chrome moly steels, okay? So P11 is like 1% chrome and 1/4% molybdenum, and the other is like 1 1/4% chrome and 0.5% molybdenum, something like that, okay? So this gives us maybe 10 times more chrome. Where would we use the P11 or the P22? Where would we use that? Extraction steam system. Why is that? Because it's two-phase, okay? It's two-phase, water and steam. So the steam accelerates the water droplets, and that even makes the FAC even worse, okay? So these are the two big issues we try to emphasize. And remember, we had 4 guys die and 5 guys die from these things. We don't want any more people die. But not only that, but it affects the nuclear safety. Whenever you have a big pipe break, a big accident, it affects the nuclear safety, okay? Anybody think of one more thing that's special for nuclear power that we don't see in the other power plant? What's one more thing that's special about nuclear? Radiation, right? So neutron embrittlement. And where do we have the neutron embrittlement? Belt line, that reactor vessel, the main cylinder that surrounds the core, right? The head and the bottom and the top cylinder, that's not so critical. But if we make sure that this one is okay, the effect on the other one's even smaller, okay? So these are the big takeaways that makes nuclear different. So let's look at the takeaways. Let's do this fast, then we all go eat dinner. I think we're hungry, okay? So what materials do we use in the nuclear plant? Carbon steel, well, steel, right? Steel and concrete, right? And why do we use concrete?
Durable.
Strong, a lot of compressive strength, right? And we can make any shape we want. And what's special about nuclear and concrete? Why is concrete good for nuclear part of the plant?
Shielding.
Shielding, right? Yeah. So it's good. So it's double acting. It makes the structure and the shielding, right? And then we use steel. Why do we use structural steel? Okay, so that's concrete, right? Where do we use the concrete? Containment building, because we might want to shield the radiation after an accident. And in the aux building, because we have a lot of radiation in the aux building, right? And what do we use in combination with concrete?
Carbon steel.
Carbon steel in the form of, right? Rebar. We call rebar, right? And why do we use it? Because concrete has no strength in tension, right? It just cracks open. So we put rebar near the surface on the top and the bottom. So if the concrete tries to bend either way, the steel takes all the tension on the top and the concrete takes all the compression on the bottom, okay? And what do we use for pressure boundary components? What material? Carbon steel. Why carbon steel? It's strong. It's stronger than stainless steel. It's stronger than chrome moly steel for our temperatures. What about at higher and higher temperatures? What happens to the strength between carbon steel and stainless steel? Carbon steel kind of loses its strength, right? But at our temperatures, for nuclear, carbon steel has a better strength. What else is good about carbon steel? It's cheaper. It's a lot cheaper than chrome, alloy. Well, it's cheaper than alloy steel and cheaper than stainless steel. And what else is good about carbon steel? It's easy to fabricate, okay? The welding is easy. If you try to weld the chrome moly steels, it's tricky. If you try to weld the stainless steel, it's hard to make welding that doesn't crack, okay? So the welds are always ready to crack in the chrome moly and the stainless steel because the chrome migrates, okay? So we get chrome moves around when you, because what does welding mean? If I take two pipes and I weld together, what does that mean? Physically, what happens? Pardon? What happens? I melt it, right? I put in energy, electrical energy. Sometimes I have a welding rod that melts, but there's so much heat. This side melts, the welding rod welds, and they all come together and they fuse again, right? But when they cool off, the chrome doesn't always stay equally mixed like from the steel mill. And so I can have chrome precipitation out, carbide precipitation. We don't get that so much with carbon steel. Carbon steel makes a good, solid weld that doesn't crack. But chrome moly and steel, so we don't want to use those if we don't have to. Why would we use them? What forces us to use these materials that's not carbon steel? Why would we use those expensive materials that are hard to weld? Some kind of corrosion. Which kinds of corrosion? Fact, right? And also general corrosion attack, like acids, right? So if we have general corrosion attack, like seawater, you want to put seawater through carbon steel for 40 years? I don't think so, right? Okay. So remember that. Always remember, carbon steel has good strength, good economy, and it's easy to fabricate. The welding, it's easy to make a very good, strong weld that doesn't crack. So those three things is why we use the carbon steel. We like the carbon steel. Even though we have a FAC problem, we like the carbon steel. Okay? Just make sure all of the steel that handles flowing fluids in the plant has 0.2 chrome minimum. Okay? The two most important challenges for integrity of pressure boundary components. I don't remember what that one was. What's the answer to that one? Anybody have the slides? I guess we were saying FAC and stress corrosion cracking. That's really what we were trying to say here. What structural properties do we want in steel? Now that we said we want steel, what do we want in our steel? We want strength, right? We want high yield strength, high ultimate strength. What else?
Ductility.
Perfect. Ductility, right? So we want good ductility. So how much ductility we can measure by elongation, right? What's elongation? What does that mean? How much percent does it stretch before it breaks, right? So a rubber band has really good elongation, right? So why don't we make our plant out of rubber? No strength, right? How much elongation do we get for carbon steel? How much percent? Anyone? 20%?
No.
Before it breaks. Elongation means how long does it stretch before it breaks? 14%.
2%.
14%. Carbon steel is 10 to 15%. How about stainless steel? Anyone? Stainless steel, how much elongation do I get? 60. 40 to 60. If you do in the laboratory, they've made steels that have 400% elongation. But that's very carefully controlled, very expensive steel just for laboratory and science, okay? So which one has better ductility? Stainless steel. Just you can see it in the elongation. Which one absorbs more energy on a Sharpie impact test? Stainless steel, the one with more ductility, okay? So we want strength and ductility. How do we make steel? How do we make, what are the steps to make the steel? We melt. What do we melt? Well, we could start with one of two things. There's two different things we could start with. What are those? Pig iron and scrap steel. Other old steel, recycled steel, okay? And when we use pig iron, we usually put some extra scrap steel in there just to get the flux working and everything working well. Okay, so we start with pig iron and scrap steel, and we heat them up till they're melted. And then if it's pig iron, it's got too much what? Carbon, right? So we put oxygen through there and burn the carbon off, and then all of that agitation raises up the slag to the surface. Slag is lightweight elements that we don't want. Calcium and phosphorus and sulfur and that. So we take those off and we're left with good steel on the bottom. We add alloy elements and then we can degas it. So we can do a second step and we can degas it, take all the gases out in the separate furnace. Then what do? We have molten steel. What happens to that? What do we call that process? Casting, right? We cast it into a slab, an ingot, right? Then what do? We can forge it, right? If we have big, thick members, we can forge it into a shape. Why don't we just pour the casting into the right shape? Well, sometimes they do that. Sometimes for valve bodies, they do that. But how thick does the casting have to be compared to the thickness of the forging? Which is stronger, a casting or a forging? Forging is stronger. Why is that? Because we align the grain boundaries. When you cast, it just kind of forms into that crystal structure that you get. But now if you start stretching and folding and stretching and folding and stretching and folding, now you align the grain boundaries. So the grain boundaries are strong. So the forging is stronger. Sometimes we just pour a casting like a valve body or a pump casing, but we have to make it extra thick because the casting is not very strong. But if we want to make a cylindrical reactor vessel, we can forge it and make it a lot stronger, okay? What else do we do besides forging?
Fabrication.
We roll. Hot rolling, cold rolling, and even have warm rolling. So if you make very thin sheets, you can just start rolling the slab into thinner and thinner and thinner sheets, right? So then we can have sheet metal for cars or other things. And then after we do that, what other process steps can we have? What kind of finishing? What do we do with finishing? We can heat it up again to lock in the grain structure and then quench, right? We could quench. Okay. We can coat it with tin or galvanized, hot dip galvanized. There's other, you can pickle it. What's pickling? What does that mean, pickling? Acid bath, right? So we form the steel into a sheet. Now we have imperfections on the surface, right? Things that we don't want. If we go through the acid bath, it cleans those off and it passivates the surface, okay? So now we pickle the surface and get a nice corrosion-resistant surface. So what are the common alloying elements that we have? Number one is what? Chrome. What's the number two one we might use in big amount? Nickel, right? Chrome and nickel, and we make stainless steel. So chrome could be 12 to 30%. Nickel could be 8 to 12%. And then we have other ones too. We have a lot of other ones. Vanadium and niobium and a lot of other ones, okay? And why do we like steel for structures? We said we like concrete because we can form it any shape and it has shielding properties and a good economy. You can make it anywhere in the world. Why do we like steel? I mean, concrete's easy. You just get a bag of cement and a bag of sand and a pile of gravel and you mix them together. Anybody can make concrete. But can you make a steel beam that easy? No. So why do we like steel? We can do long spans, right? So we can have big open spaces like a turbine building. So we like steel in the turbine building because we want a lot of space for the turbine and the lay down and the crane, right? So we can have a long beam that stretches over a long distance. And what else? It goes up very fast. It's easy to erect, right? We can fabricate most of the steel in the shop, in the factory, and ship the pieces and then just have all the numbers on the pieces. If you go in the dormitory, you go in the entrance, you can look up and there's some big steel beams. And you can look and you can say, oh, there's the column, and then there's a welded piece like this, and then there's a bolted piece with flanges. So we have a column and a welded end on the column, and then in the middle is a beam that's bolted on the top and the bottom. So you can imagine the column and the welded piece was prepared in the factory, right? And then when they came here, all they had to do was put in the bolts. So it's easy to fabricate, it's easy to erect, it's fast. What about concrete? We didn't have time for concrete. How fast is concrete? When I put up the steel and all the bolts are tight, how long does it take the steel to get strong for that structure?
Immediately.
It's already there. But how about concrete? 28 days, you might have 70% strength. And then another 28 days, you might have 80%. So concrete doesn't have strength right away. So what do we look at when we decide which steel to pick out? Pressure, temperature, and the environmental of the fluid, right? Is it an acid fluid? Is it a high velocity? Is it a two-phase mixture? Right? So we have design pressure, design temperature, minimum wall. So what two material challenges do we have for primary system? Fact. Did somebody say fact? Primary system? I hope we didn't say fact. Fact is carbon steel. If you have a carbon steel primary system, you're talking about a boiling water reactor. What do we have? What two things? Stress corrosion cracking and neutron embrittlement, right? And what are the materials we use? Well, for exposure to the surface, we have stainless steel and Inconel. Westinghouse uses stainless steel reactor coolant piping. Combustion Engineering and Doosan use carbon steel with weld overlay on the inside, right? So we can have a stainless steel or Inconel weld overlay. Sometimes they do multiple levels, multiple layers. Reactor coolant piping is carbon steel on the APR 1400. But what about the injection piping, the safety injection lines? What are those made out of? Stainless steel, okay? So we might have a reactor vessel. Throw that one away. So we might have a reactor vessel with what we call a nozzle, okay? And then we have a layer here of the overlay. But over here, we might have a stainless steel pipe, okay? So in between, we might do a series of alloys. We might have an alloy 308 that we weld to this carbon steel over here. And then we might do a weld overlay from 309. And then finally, we weld the 309 to the stainless steel. So we don't weld stainless steel to carbon steel directly, okay? So we have all those details to work out. But we use, for the materials exposed to the fluid, stainless steel, Inconel. And for the reactor vessel, we use carbon steel because it's strong and economical, and we can make good welds that don't crack, okay? Where do we find allowable stress for materials? On the primary system. ASME, Boiler and Pressure Vessel Code, Section 2. That's the other class, right? Why do we use boron in primary system water?
Control reactivity.
Control reactivity. When? Beginning of the cycle, right? We need a lot of boron because we have a lot of fresh fuel. It's ready to run, ready to go. And then by the end of the cycle, we exponentially decrease boron all the time till end of cycle. Then we put in new fuel. Then what? We start over again, right? Why do we use lithium? Because the pH is too high or too low with boron. Lithium raises or lowers pH? It raises.